Okay, I see most of you are already here. Great, let's get started. So what we're gonna do today is to discuss the lecture number 6.7. So I will talk about 6.6 in the end when we finish talk about 6.7. So today's aim will discuss the distribution for end-to-end distance and segment density. Okay? So before I start, I need to ask a couple questions to the audience regarding, since we already thought about a lot of chain model, many parameters to quantify your chain dimension, not only just the end-to-end distance, but also radius of gyration, persistence length, and why do we need to learn a new parameter about the chain dimension and talk about distribution of end-to-end distance? Please, and anyone have an answer to that? Sure. So, Brian, the question is, we have discussed many parameters to talk about average end-to-end distance and as well as average Gaussian coil size. Why do we need to care about the distribution of end-to-end distance?
Because in the case of average end-to-end distance, it only concerns 2 points. So in molecules with more than one endpoint, that may not be the most accurate parameter. Plus average end-to-end distance is hard to measure on its own. So in taking a more broad average, we can provide a more generalized model for the molecule.
You're kind of right, but there is one more important thing is your molecule is not frozen. Your polymer chain is not frozen, in other words. So think about the case where you have a polymer. Think about it's like a coil dissolved in water. It's like a worm. It will move around, it will change shape. So at a certain snapshot of your picture, your behavior of the polymer chain may be not following the prediction of your end-to-end distance. Okay?
Based on the idea of, I'm sorry, I didn't mean to interrupt, sir.
Oh, go ahead, Ryan.
Were you asking a question or were you about to say something? I'm sorry.
I'm going to continue to discuss what I was talking about. So what then, that is becoming an issue because at a snapshot, for example, if you want to get an average size of me sitting in front of TV, sometimes my arm is wrapped around my body, sometimes I extend it. So average distance is a good way to get a good idea about what is time average or number of molecular average for a certain dimension or size. But it is not going to be representative if you were able to frozen in time and look at what this molecule is behaving at that specific time. Okay? So that brings down to today's topic. So we're going to learn, address one question is, what about the distribution of end-to-end distance? We can think about the problem in 2 ways. We have discussed those 2 ways sort of briefly in previously. You can think about 2 ways. First is you can think about one single molecular, how does it move its shape or change its shape over time. So if you think about the polymer, it sometimes randomly the end-to-end distance fluctuate and get closer. Sometimes they're going far away. So you can take a time average of that. That would give you average end-to-end distance, right? So you think about average over few hours for the chain conformation, what it will be look like. That's one case. The other case you could think about is you have lots of molecular, they are identical, they are dissolved in solvents. So if you take an average of all the molecular at a certain time snapshot. So in other words, we could do as an example, for example, we have now 16 students, each representing a polymer chain. So if you think about now I take a screenshot, then that would be an average of everybody. That will give you average end-to-end distance. Or I could take average the video of myself over a period of 1 hour. That would also give you some good idea of what the end-to-end distance is. So first is, what would be the distribution of the chain ends? First, let's talk about the probability where you find a chain at a certain distance. So that comes down to the first lecture we did. If everybody recall, when we introduced the class, we discussed a concept about random walk, right? We discussed about 1D and 2D random walk, and the distribution can be easily interpreted using a 3-dimensional random walk. What this means is, if you know how does your polymer chain behave in 3-dimensional space at a certain time slot, you can use a 3D random walk, not necessarily the self-avoiding walk. We haven't gone into that part. 3D random walk, you would be able to get what would be the time and space where these molecules would be, okay? I will first talk about the physical concepts, then I will go into a little bit more detail, explain how people actually get this distribution function, okay? So the distribution function is already shown here. So let me explain this particular equation. In here, you can see the probability P is a function related to a prefactor. So here it shows the prefactor. It will be 3 divided by 2 pi mb squared, power of 2/3. Everybody knows what each individual component mean, right? So these are constant. These are numbers and constant pi. What changes as mb squared? And mb squared is what we already know is defined as end-to-end distance for ideal chain. So if your polymer is chosen, this end-to-end distance mb squared will be fixed, so you won't need to worry about this part. It will be a constant. So you can think about this, everything before this exponential will be a constant. And then in the exponential, it follows a Gaussian distribution because it's exp exponential minus r squared. R is where the distance from your molecule to the origin of the x. So if we go here, r is basically defined as the distance from your 0 position to here. Okay, this would be defined as r. So in this case, if you see this r is here, right here, and if r is smaller, your distribution, if you, based on this equation, you will see r will be allowing to higher distribution probability. If I plot a probability p versus distance r, we have discussed this will be a Gaussian distribution. It actually will be a perfect half of the Gaussian distribution because you would have highest chance happening at 0 position, which means your chances of finding your chain will be highest to where it's closer at its initial position. And you might be curious, this seems contradictory to what we have said in previous lecture. Average end-to-end distance will be equals to mb squared. And wait for it, we haven't discussed, this is only talked about distribution, where you can find the chain end. It's not the distance, okay? It just talk about where you can find the chain end. The distance will be needed one additional term, and you need to integrate the distance over the space you need to find it. And how do we define the probability of finding a chain end? That is can be defined as the distance from the center of your origin to where the distance r circle is. So in other words, if I were able to draw, in this case, if we have h is given, the distance from the center. So if we want to know if there's any chain distributed around here, we need to consider a circle, as shown here, with the distance dh. dh means if we increase the h by a little bit, that means we increase the length by a little bit. How big is the chance we can find it? This will be defined as you can see, that area or the volume is defined by 4 pi h squared dh. That's the surface area of your sphere, and dh is basically the increase the length of the sphere. Okay, so what this term is talk about, all these, what I highlighted is red, all these regions where you can find your chain end. If you combine these two, you would be able to get a newer distribution function. That would be this will be a new distribution function that will be equal to 4 pi h squared multiplied by p. Then this will be r. And now you can see that there is a highest is the chance of you finding the chain is no longer at 0 position. And this specifically highest is chance would be equals to exactly the end-to-end distance will be n b squared take a root. Okay, so let's speak a little bit more simplistic language. So in other words, when you have a polymer chain, when you stop and look at the polymer chain at a given time, you have ability to find it here, or here, or here. As the end-to-end distance can be very narrow, can be very long. But the chances you have long distance is low. Why? So think about the case where you need to find a long end-to-end distance, much bigger than what you had in mb squared. That means your chain is extended. Okay, your chain is actually happen to be in a very extended form. The chance of finding that is low, because if you let it go, the entropy will relax the chain back to where it's mb squared position. Okay. So with that being said, what we have discussed in previous about average end-to-end distance is still quite important, because we take a statistical average for everything. And it is not just one specific position or time. It talks about average, so it's more representative to what we are sampling in your polymer. If you just take a camera, look at one time, your end-to-end distance may be very narrow, but it's not representative. Same here for higher value. So that explains why it's also important to look at the distribution of chain ends. Okay. So we can also do a little bit calculation to help everybody understand a little bit of what is a distribution and as well as chain end distribution and end-to-end distance. So, hey.
I have a question.
Yeah, please, Kundu.
Sorry, I tried to raise my hand and
No, just please ask. I actually cannot see if you are raised a hand or not. So if you have a question, just speak to me.
Thank you. Can you please go over the two different figures that you said, and can you reiterate that again to me? Thank you.
Which part?
The two different figure where you focused on the first part where the finding the project polymer chain is more on the center area than the farther away, and the other
sure.
That says not. Thank you.
I believe we are discussing the particular this curve on the bottom right. So do you understand why there is two differences of end-to-end distance distribution versus end-to-end average end-to-end distance? Those two are the difference. Okay, so let's go back to this one and let me explain the probability one more time. And it's probably easier to go through what we have talked about previously. So let's go quickly use a 2D random walk to explain. Okay, 2D random, maybe even simpler. Let's do a 1D. So if you have axis, you can take a plus. You can take steps so that can end it up with different position. Let's say I am asked to move around the classroom. I can take either a positive step or negative step. That if I take 3 moves, what would be the end position I could be ended up? So I think this is a easy one for everybody to visualize the distribution. So if I take 3 moves, each move I have 50% of taking +1 or -1 because it's random. What is the chances I would end it up at where I start off at position 0? If I take 3 steps? Anyone? It will not be. You won't be able to reach position 0, right? Because you are taking 3 steps, and each step will be either plus or minus, and you always ended up with an odd number where you ended. So let's start with a simple case. I'll walk you guys through. If I start with position 0, if I take a 1-step move, I would have a 50-50 chance ended up with -1 or +1. Because I can go either way. If I take 2 steps, then you would have more distribution. You could end it up at -2, and you could end it up 0, or you could end it up +2. So now it's interesting. You will have different chances of reaching each region. Take 2 steps. You could either take a positive step, then a negative step, where you will end it up at position 0. Or you could take a negative step, or then a positive step. So you have 2 routes you can reach to 0. And you have each one route to take it to +2 or -2, because in both cases, both steps need to be positive or both steps need to be negative. So you would end it up at 25% of chances at finishing at -2 and 25% chances of finishing at +2. And you would have about 50% where you're right in the middle. Okay? And why it's 50? Because I explained you have 2 ways you can reach it. Either take 2 steps, either take a positive step first or a negative step first. So what we have talked about, we ask it, how about 3 steps? And you will quickly realize you can have -3, -1, +1, and +3. Right? So what is the chances of you finishing up at -3? Can anybody help?
Would it be 12.5?
Oh, Brian, you nailed it. Why 12.5?
Because there are 2 methods of getting to -1. You can go from -2 to -1 and from 0 to -1.
Okay, so what are the chances of you finishing at, you ended up making 3 moves and end at -1?
25%.
Say that again?
I'm sorry, not 25. It's 25 plus 12.5, which
Oh,
sorry.
yeah, perfect. So you got it. And why? Because you have now multiple ways you can reach that. You would have ability to take a negative step first. So you would be able to go negative, then to positive. You would be able to positive, negative, then positive. Ended up at 1. And you would have 1, 2, and minus 1. You would add it and end up at 1. So we can generalize this relationship. So the total steps you would take, we don't need to take 1 more 4 steps, but I'll use it as an example. You would have total number of opportunity would be 2 power of force. So that would be, you would 16 variations to reach it, right? And then it doesn't matter if you take a positive or negative first, but as long as you take a 2-step positive, 1-step negative, you will end it up here, right? So wherever you're ending, you need to consider a factorial. So I assume everybody knows a little bit about factorial, what that means. So let's say 3 factorial will be equals to 3 plus 2 plus 1 would be 6. So that's what factorial means. So now, what would be the chances we ended up at 0 for 4 steps? It's a question you can simplify by 2 power of force. To end it up 0, that means you need an even split between positive step and negative step, right? So if you cut 4 into half-half, that means you can take 2 factorial multiplied by 2 factorial. Okay. Does that make sense to everybody? Or if I need to slow down a little bit more, let me know. Okay? So that's basically explained. And if you keep doing what I'm showing, you will see that at the end position we plot as probability, where we plot the position x. You would have highest the chance at finish at 0. If we just increase in, this would be chances of number n step. We keep going, it's gonna spread, but it will take this Gaussian shape at the end. And you ended up at very high value will be low, because you need to keep, it's like throwing a coin, you need to keep hitting heads so that you can keep advancing, right? If you flip it, you hit a tail, then that represents -1, you would not be able to reach here. So if you ended up with n step and all positive, it will be as low as 1 divided by 2 power of n. If n is 100, that is almost unlikely you will be able to reach that. Okay? So that explains the distribution. Does it make sense to you? Can you provide some feedback, Kongdu? Okay.
Yeah, I understand now why it's, we can find more variety.
Right. So let's keep it. Okay. So now, the second curve, 4 pi h squared multiplied by p, and p is only the probability of finding it. It doesn't represent the distance, right? If you need to consider a distance, you need to multiply the distance to the probability and integrate it over the region of your finding. So this particular sphere we show in here, it discusses what the chances of you finding the molecule inside this ring. So this will be a three-dimensional ring that has a surface area of 4 pi h squared. That's just the surface of the sphere, and this is just a college math, I assume. So 4 pi multiplied by h squared. H is the distance, will give you the total surface area in this red ball. And we need to integrate over this surface area, see how many chains happen to be in that area. So that's why we need to do this. And once you multiply this factor, you will see when your distance h is 0, although you have a very high probability, right? You have high probability, but because the distance is low, it will result in a lower distance, lower end-to-end distance in this case. And you will hit the local maximum because, oh, sorry, accidentally touched the screen. This will be representing the maximum in chances of you finding a polymer chain at a certain distance. And the more you go, the 4 pi h squared term goes up because probability term goes down. When you multiply by these two, you would also have a minimum here. Okay? All right, does it explain to you what this is trying to do in explain what is a random walk and how we can use that to understand distribution of the polymer chain? I think distribution is important in a sense that it's more realistic, right? If you pull a random chain out of a solution, it won't be exactly at end-to-end distance what we predicted. But with time or with number of its friends in the neighboring hole, if you take an average, you would get average end-to-end distance. Okay? That's pretty much summarized. The textbook, it has a little bit more bones into it. It's explained the mass, how they reach that. I'll do a separate section to do all the derivative for everybody, but I don't think we need to go too much deep in the math in the classroom. It's to be honest, it's quite demanding in the math what they are trying to do. But for those who are interested, let me know. I'll show you what that means. Okay, so regarding distribution, I think the key take-home message is you need to understand why there's distribution and how does distribution affect your polymer's behavior. Next, we're going to cover a little bit about chapter 6.6. This is a chapter discuss about a very broad title. It talks about sphere, rods, and coil. So anybody has read this and can give me some of your thoughts why we call them sphere, rods, and coils? Oh, very good guess, Brian. Anyone else? Anyone else has something to guess? I can give you guys a hint that even for the same polymer, it would change its behavior. It could encompass both sphere and may not be rod, but also the coil. I think sphere and the coil is easier to explain. Everybody recall the first lecture we did. So in the first lecture, we talked about a tennis ball and a football court, and those two are the relative dimension you can achieve in the polymer physics with regarding a polymer coil in a good solvent and in a very terrible solvent. So you can imagine that the polymer will adopt a coil shape. A coil is a very common description for the polymer, but if you add a non-solvent, something really bad and something doesn't dissolve your polymer coil will crush out and form a sphere. In this case, the sphere will be related to what we think it's compact state. And we have discussed how we can use the density of the polymer to calculate out what's the volume it would occupy. If you have forgot that part, feel free to go back to the first lecture and you can check that out. in terms of what is sphere and rod. So the other thing that we need to cover is the rod. So in what case polymer would behave as a rod?
When the average bond rotations all happen to adopt a trans, or the vast majority of them happen to be trans as opposed to Gauss plus and Gauss minus.
There will be as we talk about today, there will be a specific time. Yes, that's possible, Brian, but it's not possible with other energy state. Let's say if your polymer has been heated up, or if your polymer is being relaxed, it might adopt other configuration. So rod and coil is specific, talks about polymer with rigid bonds in the backbone, so you don't allow any rotation. Some of the recent work, people discuss what is the rod-like, or even discuss the ladder-like polymer, where you wouldn't have any rotation ability. You would have literally double bonds along the backbone all the way, so there's no any rotation. In that case, you can regard your polymer as a rod. That means it's pretty rigid, and you would have you wouldn't have any rotation, and this will be reflected in the persistence length. DNA is a good example. Like in the textbook they show, you would have persistence length up to 60 nanometer. But there is one more thing that is more important for everybody to consider, is that is related to some theory regarding the scalar relationship. Okay. Actually, I have another textbook that I just put next to me. So this is one for whoever is interested. You should be able to see it. It's called Scaling Concept in Polymer Physics. I don't pretend I can pronounce the name of the author. He is a French scientist. His family name is Distribu. And one of the things that unique to him is he invented an idea that actually, as a polymer scientist, you don't need to go down to be understand all the specific numbers. What important is you could only understand the scaling relationship and predict if your polymers is a rod or coil or sphere. And how does this scale relationship works? Let me explain this part. So, what is scale relationship? So in normal cases, we would, can everybody see the writing okay? So in the normal cases, we know end-to-end distance square would be equals to mb square, or r would be right? So you would have a b. Can everybody see the screen okay? Is it flipped for some reason?
No, we're good.
Okay. Okay, you can see. So this is a good equation that r would be equals to n power and half and b, right? But in some cases, can everybody understand what this means? Instead of we use equation or we use this symbol, and that means proportional. What that means, your end-to-end distance r will scales with n power of 0.5. That means if n increase by 2, r would increase by root 2. Okay, so you know how fast it depends. If you plot log R log n, you would have a linear curve, and this slope would be equals to 1/2. It talks about how fast you can increase and expand. In another case, when we talk about other scaling relationship, so how about this would be the coil. How about in the sphere case? For scale relationship. In this case, how does would be n? R depends on n. Anyone have any thoughts? I can tell you it's definitely not 0.5, because that would be related to what we talked about is ideal chain, right? So if it's not 0.5, first let's see if it will be smaller or bigger than 0.5 and why. Okay, any volunteer?
Can we get bigger?
Bigger, so it has stronger dependence. Okay, I heard one volunteer. Anyone else would hit? No one is taking a bet it will be smaller or weaker dependence? Okay, I would take the second one, and I'll explain why that's the case. Well, if it's already a compact sphere and everything is condensed, we know your volume or end-to-end distance will be dependent on n, because it's a condensed phase, and we know the volume of a sphere would be equals to, right? This equation, I think everybody can understand the diameter, the radius of your sphere, and how does it relate to the total volume of your sphere. And in this case, because we said it's a compact disk, we know that the volume will be equals to number of bonds multiplied by density and some another constant. And if we consider a scaling relationship, those are constant, so we don't need to consider any constant. So n would be proportional to r power of 3. And if you rearrange it, you can get r would be proportional to 1/3. So it's quite brilliant, right, for this person, Dijon? He's very smart, so that he can get a Nobel Prize in polymer physics. There is not many Nobel Prizes in polymer research, so he's one of them. And as you can see, his contribution in this scaling relationship is very simple. So we know this will be now 1/3 in the case of the sphere. That's pretty straightforward, right? The other thing we can discuss about is in a good solvent. So we talked about ideal chain, we talked about compact. How about rods? We haven't discussed about rods. How does end-to-end distance would depend on n? Okay.
It would be directly proportional to it, and it would be equal to n, guess n, because the number of steps, because it's like a rod, the number of steps would guess directly impact the end-to-end distance.
Good job, Brian. How about we have one more question? How about real chain? What we have discussed up to now is all ideal chain. And I specifically mentioned several times, ideal chain doesn't consider overlapping of the polymer. So real chain, what you think about dependence on N? Again, I'm gonna use ideal chain as example. Would it be bigger or smaller, weaker dependence on N? And think about what we have shown in the rods. It will be strong dependence, r to the power n power of 1, and in the idealized chain it's dependence of n power of 0.5. So and compact chain will be dependence of n power of 1/3. So where the real chain would sit? Larger than 1/2. Zoe, good job. And we will discuss a little bit more detail in the next lecture. How can we address this real chain, dependence of real chain, and why that's the case? What I can show the result is today is, well, I will talk about conclusion. It will depend of n of power of 0.6, and 0.6 is approximate. If you want to be more precise, it will be 0.589, but for the simplicity, people just use 3/5 or 0.6 as dependence. And you can see it's stronger dependence on N. That means your chain is expanded compared to a real idealized chain for your real chain. And I think the concept we mentioned many times because of excluded volume effect. So in the next lecture, we're going to discuss how we actually were able to get this this value and what consideration we have. So there's two competing forces are balanced out due to the good solvent. So one is expansion due to excluded volume. The other is due to the entropy when you stretch a chain. So in the next lecture, we're going to quickly discuss that. So that summarizes also what we have talked about in this sphere, rods, and coil. So in the next lecture, we're going to talk about a little bit about self-avoiding chain, a first look. So that will talk about basically what would be the real chain and why its dependence is stronger than 0.5. I think I'm gonna wrap up here for today's lecture, and we're gonna leave some time for Q&A for the radius gyration as well for this class. So if anyone have questions, it's a good time to ask now.
Hey, Dr. Gu, have you uploaded these slides yet in the PowerPoint format? Because the PDF still has the issues with the formulas.
Oh, I have not, John. I apologize, and I'll send it up there. I'll send it probably as a PowerPoint. I tried it again last time. It sends a Mac issue whenever exported. It will be the same, but PowerPoint it should be fine. So it will be slightly bigger size, but you will be able to see them. Okay.
I've also noticed that like some of the slides don't seem to go in the same order as you have been in the lecture, so it's a little confusing. But
oh, yeah, some of them I found it's a little bit outdated. I would say some of them are too complicated in a sense that it doesn't help everybody to understand the term what we want to discuss. So I rearranged maybe 1 or 2 slides or omitted 1 or 2 slides, but most of them are almost the same. But good point, John.
I have a question about the distribution graph, the one that has a maximum.
Yeah.
So I noticed that like the one in the book and the one from our homework both went, or not necessarily the one from our homework, but the one from our homework went up to like 0.3 on the x-axis. Is that like normal? Is that how high they normally go?
That depends on number of bonds, a couple of factors. So Zoe is talking about figure 6.13, and in the textbook they have 2. If you look at there, all these values are normalized by a prefactor. Like, let me show in here. So Zoe, so this term, if you don't have this term, this will be also a Gaussian distribution. But the probability, if you integrate the term, only have the right side, it will not be a probability of 100%. There will be something bigger than that, which is not ideal in statistical term. So that's why this is shown here to normalize it. With this term in the front, this is a constant, by the way. When you know your number of bonds, your B value, this will be a constant. So once you add this term, and then you integrate the probability over the R value, you would ended up with a perfect number 1, or 100%. That means your distribution is normalized. In the textbook, depends on what N value and B value, your probability can have more distribution. And you're right, in 0.03, that's only 3% you will be there. But that is the peak. Remember what your chance of average end-to-end distance will be integrated for all the values around these. Okay?
Okay.
And it will depend on what N value is. N value will influence the shape of the curve. So if N value is smaller, everything will be squeezed to the lower end of H. Yeah, good one, Zoe. Okay, anyone else?
I have a question, sir.
Please.
So, what we basically went over was the scalar relationships for random coils, spheres, rods, and real chains in that order.
Yes.
Okay, I just want to get that clear in my notes.
So,
Also,
so you want me to review those values one more time?
I understand what they are. I just want to make sure I got them in the right order.
Sure.
We did random coil, then we did it for spheres, then we did it for rods, then we did it for real chains in that order.
Yeah. In the lecture, yes, but it's not necessary you need to follow the exact order. It's just the way how I thought about can be easy for everybody to understand individually.
And the two graphs you did, the first one was for the average end-to-end distance, and the one was the average end-to-end distribution.
No, the first is a probability for the end-to-end distribution. So it's just a probability. It not necessarily have distance term. The second term is distance term because we multiply by the surface volume of the sphere to find it.
So the first one is just the probability of end-to-end distribution.
Yeah. So the first is probability where you find the chain end. The second one is probability for distribution of end-to-end distance.
I'm sorry, just the way you said it, it just made it sound like they were the same thing. The first one gets...
No. They're not. One is a probability, the other is distance. If I said it incorrectly before, then this is the right one.
Okay. Well,
I have another question.
Yeah, please, though.
Are you going to tell us where the cutoff of info is for the exam?
What that mean, cutoff info? Where are we going to cover?
Your lecture, like everything before this point is on the exam?
Yeah, so it will go by chapter. So everything on chapter 6 will be on. Nothing will be on chapter 7, so only chapter 6.
Okay, all of chapter 6.
Right.
And then, okay, and we will be done with chapter 6 lectures before the exam, correct?
Yeah, so we're going to have one more lecture next Tuesday. Then Thursday, we're going to use the time to go through the homeworks. And I will explain all the homeworks and give everybody some time to study. Then the next Tuesday. So 3 classes from now, we will have a test. Okay? And the test will be open textbook test. I think it doesn't make sense for the remote test to close the book, so you can relying on the textbook. It will cover several aspects. It will cover the concepts, so that means what will be discussed, explain what you know, knowledge about a certain scientific term. There will be multiple choice, there will be calculation test or numerical question. Okay, hope this helps.
Yeah, that's good. Got it.
Okay, so Brian still raised the hand. Brian, do you have more questions?
I'll put that down.
Okay, no problem. You can keep it. Anyone else? Especially the question regarding the radius of gyration. I think last time it was not the right format, but it's basically fairly straightforward, right? RG is another term that describes end-to-end distance, but very easy to measure. I hope everybody gets that part. I think the homework is very challenging. I got some email from some of you, so use this opportunity. It's like running a marathon, so this will be the final push. If you can get all the homeworks and spend your time to think about it, you would easily passing the exam with flying color. Okay. All right, if no more questions, then I'm gonna wrap up here. Again, the lecture today will be uploaded to the YouTube. If you ever need to watch it again, or if some part is not clear, I'll upload later today and you can see it. Otherwise, I'll see everybody on next Tuesday, okay? And next Tuesday, we will cover the last part about the real chain and how does polymer behave in real world in solution. And that will be the last of this lecture. Okay, then bye-bye everybody, and I'll see you soon.